Right now, 3.5 astronomical units from the Sun, where ice should stay frozen and comets should be dormant, an interstellar visitor is hemorrhaging 40 kilograms of water into space every single second. That's more than 3 times farther from the Sun than Earth is. Out there, sunlight is a whisper. At that distance, our solar system comets go silent. They freeze solid. They wait, but not this one. This Comet Catalog designation, 3I Atlas, was discovered in early 2025, just as humanity's detection capabilities reached unprecedented levels. Swift Space Telescope turned its ultraviolet eyes toward this interstellar wanderer and saw something impossible, a brilliant halo of hydroxyl molecules, the death echo of water molecules being torn apart by distant sunlight. This shouldn't be happening. The physics don't allow it. Yet the evidence screams across space in wavelengths of light our eyes can't see, but our instruments detect with perfect clarity. Tonight, we're going to explore this mystery together. We'll examine what we know, what we suspect, and what remains unexplained. We'll trace this comet's journey across light years and billions of years. We'll investigate chemistry that doesn't match our solar system's rules, because understanding this anomaly could reveal how different planetary systems create comets, or it could challenge everything we think we know about volatile chemistry in space. The stakes are profound. Every interstellar visitor is a message in a bottle, a cosmic postcard carrying information about conditions we can't directly observe. And 3I Atlas is speaking in a language we're only beginning to understand. So settle in. Get comfortable. Let's follow this mystery wherever it leads. Picture this. You're floating in the cold silence of space more than 3 times farther from the Sun than Earth is. Out here, sunlight is a whisper. Ice stays frozen, comets go dormant, everything sleeps. And then you see it, a comet absolutely hemorrhaging water into the void, pouring 40 kilograms of the stuff into space every single second. Not a trickle, a flood. Water gushing off a frozen rock where water has no business flowing at all. This is 3I Atlas, an interstellar comet that arrived in our solar system from somewhere else, carrying rules from another star's backyard. And those rules, they don't match ours. The first clue came from Swift Space Telescope, designed to hunt gamma-ray bursts across the universe. In early 2025, Swift turned its ultraviolet eyes toward 3I Atlas and spotted something impossible. A halo of hydroxyl molecules surrounding the comet like a glowing shroud. Hydroxyl, or OH, is what you get when sunlight rips water molecules apart. It's the echo of water screaming as it dies. When you see OH, you know water was just there being torn to pieces by photons. And Swift saw a lot of it. The numbers are staggering. At 351 astronomical units from the Sun, 3I Atlas was releasing 1.35 x 1027 water molecules every second. That's 40 kilograms per second. Every second, like dumping a small car's worth of water into space every minute at a distance, where our comets barely whisper. Our solar system comets don't do this, not out here. This far from the Sun, they're cold, dormant, practically dead. Water ice needs heat to sublimate, to turn directly from solid to gas, and there's just not enough solar energy this far out to drive that kind of activity. Our comets wait until they're much closer before they wake up. 3 Atlas didn't get that memo. You might remember Oumuamua, the first confirmed interstellar visitor. That thing was dry as a bone. No water, no outgassing, just a tumbling rock speeding through our neighborhood. Silent as a ghost. Then came 2I Borisov, the second interstellar comet. Borisov was active, but it behaved exactly like our comets do. Predictable, boring in the best way. 3I Atlas is neither of those things. It's alive in a way that shouldn't be possible. It's screaming water into space where silence should reign. What mechanism could possibly drive this? Is there some exotic ice we don't know about? Something that sublimates at temperatures we thought were too cold? Is the comet's interior still warm from its birth? Is it rotating in ways that focus sunlight onto hidden reservoirs? Or is there chemistry happening inside that rock that we've simply never encountered before? The water is just the beginning. 3I Atlas is also leaking cyanide nickel carbon dioxide in concentrations that make no sense. Each new observation adds another layer to the mystery. Each spectral line is another question mark. This isn't just a comet behaving oddly. This is a comet operating under completely different physical rules, rules written in another star system under different conditions with different chemistry. And now it's here giving us a front row seat to processes we've never seen. The thing that keeps astronomers up at night. If 3I Atlas is doing things our comets can't do, what does that tell us about where it came from? What kind of star system builds comets like this? And most provocatively, is this comet just weird? Or is it a messenger carrying news about how different the universe can be? Every telescope that can see this thing is now pointed at it. Because 3I Atlas isn't just a curiosity, it's a window, a crack in our understanding, and through that crack we might glimpse something extraordinary. But here's what keeps me awake at night, listening to the silence between the data points. This comet has traveled across light years.
It has survived conditions we can barely imagine. It has crossed the vast cold desert between stars. And now, just as it passes through our neighborhood, it's showing us behavior we've never witnessed. The universe, it seems, still has secrets. And 3I Atlas is whispering one of them into the void 40 kilograms at a time.
Comets are supposed to follow patterns. When they heat up, metals sublimate. Iron and nickel show up together like old friends. You see one, you see the other. It's a cosmic constant. Except 3I Atlas didn't read the textbook. The Very Large Telescope in Chile aimed its spectrograph at 3I Atlas and found something that made absolutely no sense. Nickel emission lines were blazing bright in the spectrum. Strong, unmistakable, impossible to ignore. And iron. Either absent or so weak it barely registered. Nickel without iron. It's like finding smoke without fire, footprints without feet. In our solar system, this doesn't happen. When a comet heats up enough to release metals iron and nickel appear in predictable ratios because they're locked together in the same mineral structures. But 3I Atlas apparently formed somewhere that plays by different rules. At around 2.8 astronomical units from the Sun, astronomers measured nickel pouring off at about 5 grams per second.
That doesn't sound like much until you realize it's continuous with iron nowhere to be found. That's not a glitch. That's a pattern. Several explanations have been floated, none simple. The first is chemical fractionation. Maybe in the environment where 3I Atlas formed, nickel got incorporated into volatile compounds that vaporize easily, while iron got locked into refractory minerals needing much higher temperatures. Picture nickel hitching a ride with volatile ices while iron stayed behind in rocky grains. Another idea involves organometallic compounds. On Earth, we have molecules like nickel carbonyl, NiCO4, where nickel atoms bind to carbon monoxide. These compounds are volatile, evaporating at relatively low temperatures. If 3I Atlas formed in an environment rich in carbon monoxide and other organics, maybe nickel got trapped in these kinds of molecules during its formation.
When sunlight hits them now, billions of years later, they decompose, releasing atomic nickel into the coma. Meanwhile, iron remains locked in solid grains, never having formed these volatile compounds. Then there's space weathering. Cosmic rays and ultraviolet radiation bombard interstellar objects for millions or billions of years. That kind of sustained assault can alter surface chemistry in weird ways. Imagine radiation creating nickel-rich surface layers through some process we don't fully understand while iron gets buried or chemically altered. Maybe the nickel we're seeing is a radiation-damaged rind that doesn't reflect the comet's true bulk composition. Or maybe, and this is the most exciting possibility, 3I Atlas formed in a stellar system with genuinely different elemental abundances. Stars don't all have the same chemical makeup. Older stars from different parts of the galaxy, stars that formed from gas clouds enriched by different types of supernovae, they all have slightly different recipes. The abundance of elements varies depending on the star's age and where it formed in the galaxy's chemical evolution. Maybe 3I Atlas comes from a place where nickel was more abundant relative to iron than it is in our neighborhood. Maybe its birth star was chemically odd, and that oddness is now written into every molecule of this comet, written in a language of atoms we're only beginning to read. But we have to be careful here. Spectroscopy is hard. Detecting faint emission lines against a bright background is tricky. There are thresholds of detectability. It's possible that iron is there just below the detection limit. Maybe the iron emission is blended with other spectral features. Maybe we're looking at the wrong wavelengths. As the comet gets closer to the sun and heats up, more iron might start appearing. That would be reassuring in a way. It would mean the universe still makes sense. It would mean we just needed better observations, more sensitive instruments, more patience. But what if it doesn't? What if 3I Atlas gets all the way to perihelion, the closest point to the sun, and iron never shows up? What if the nickel-to-iron ratio stays completely inverted compared to everything we've ever seen? That would be revolutionary. That would tell us that planetary systems can produce comets with metal chemistry so different from ours that our models need complete overhauls. It would mean the galaxy is more diverse, more variable, more surprising than we ever imagined. This is why astronomers are watching 3I Atlas so obsessively. Every observation is a test. Every spectrum is a chance to either confirm our understanding or shatter it. And right now, 3I Atlas is doing more shattering than confirming. Here's what keeps me up at night. Metals tell stories. The ratio of one element to another is a fingerprint revealing the conditions under which something formed. If 3I Atlas's nickel anomaly persists, we're holding evidence about a star system that might be billions of years old and thousands of light years away. We're reading a story written in atoms about a place we'll never visit. And the story says, not all star systems are like ours. Not all comets follow our rules. The universe is vast, and in that vastness, there are chemistries we haven't imagined. 3I Atlas is one of those objects, and whether its secret is prosaic chemistry or something more exotic, the act of investigating it, testing hypotheses, ruling out explanations, that's the beauty of science. That's humanity at its best, staring at something we don't understand and refusing to look away. Comets are supposed to brighten gradually as they approach the sun. More sunlight, more heating, more sublimation. The relationship should be smooth, predictable. 3I Atlas apparently never got that memo either. Observers noticed something strange about its color. Early on, the comet looked relatively neutral, maybe slightly reddish. But as it moved closer to the sun, it started turning green. Not subtle, a vivid, eerie green that became unmistakable. That green comes from two sources, cyanide molecules and atomic nickel. Both emit strongly in the green spectrum, and both started ramping up dramatically as the comet warmed. But here's where it gets strange. The brightness increase wasn't linear. It was superlinear emission lines intensifying faster than simple geometry would predict. When you halve the distance to the sun, you get 4 times the sunlight. But 3I Atlas's emissions were climbing even faster. Astronomers call this switch-on behavior. Imagine a temperature threshold. Below it, particular ice stays solid dormant. Then the comet crosses that threshold, and suddenly sublimation jumps. New emission lines appear. It's like flipping a switch. 3I Atlas seems to have multiple switches. The water turned on first at 3.5 AU. Then came cyanide and nickel as it warmed further. Each emission suggests a different volatile reservoir being tapped. One model that might explain this involves extended icy grains in the coma. Instead of all the activity happening at the nucleus surface, imagine small ice grains being lifted off the nucleus by escaping gas. These grains float away from the comet, still cold, still frozen. But as they drift outward, they're exposed to more and more sunlight. Eventually, each grain reaches its own personal threshold and starts sublimating.
This creates a distributed source of gas, not just from the nucleus, but from a cloud of icy grains surrounding it.
That could explain the superlinear brightness increase and the sudden appearance of new emission lines. You're not just watching the nucleus warm up. You're watching thousands or millions of tiny ice grains reaching their sublimation points, one after another, creating a cascade of activity. Another possibility is thermal fracturing. Comets are dirty snowballs, mixtures of ice and rock. When one part heats and expands while another stays cold and contracts, stresses build. Eventually something cracks. When ice cracks, it exposes fresh material. Suddenly, you have new surface area sublimating. The comet might be cracking itself open, continuously revealing material locked away since formation. Then there are exotic ices. Water ice sublimates at one temperature, carbon monoxide at much lower, carbon dioxide somewhere between. If 3I Atlas is layered like an onion with different ices at different depths, then as it warms, you'd see a sequence of activations.
First, the supervolatiles, then carbon dioxide, then water, then finally the stubborn stuff. This isn't entirely alien to us. We've seen comets do weird things, sudden outbursts splitting apart, staying dormant until very close to perihelion. But 3I Atlas is doing this on a schedule that doesn't match our experience. It's alive at distances where it should be asleep. As 3I Atlas continues inward, will more switches flip? Will we see new molecules? Will the activity plateau or keep accelerating? Every week brings new data. This isn't a steady comet. This is drama unfolding in real time.
Every object in space carries a story written in its trajectory. Where it's going tells you where it's been. And 3I Atlas's trajectory is telling a story that spans billions of years and thousands of light years. The orbit is hyperbolic. That's the technical term for an open curve, a path that doesn't loop back. 3I Atlas came from interstellar space, swung around the sun, and will leave again, never to return. The eccentricity is greater than one meaning. This comet is unbound, a free agent, a wanderer. It's just passing through our neighborhood, and once it leaves, we'll never see it again. Astronomers traced its path backward using pre-recovery images. Pre-recovery is when you search old survey data for images of an object before anyone knew it was interesting. Turns out, 3I Atlas had been photographed multiple times by automated surveys, some images going back to when the comet was 6.4 astronomical units away, still inbound, still cold and distant. Nobody knew what they were looking at then. Just another faint smudge in a database containing billions of faint smudges. But by stitching together these observations, astronomers reconstructed its trajectory with increasing precision. They calculated its velocity, its path through the solar system, the angle of its approach, and then they ran the calculation backward, tracing where it came from. The trajectory points outward, back into the galaxy, but not just anywhere. Orbital modeling combined with data from the Gaia Space Telescope, which has mapped the positions and motions of nearly 2 billion stars, allows astronomers to make educated guesses about where 3I Atlas might have originated. The answer is surprising. The galaxy has structure. The stars aren't distributed randomly. Most stars, including our Sun, live in the thin disk, a relatively flat plane of younger metal-rich stars orbiting the galactic center. These are the stars you see when you look at the Milky Way arcing across the night sky. But there's also a thick disk. The thick disk is a population of older stars that orbit in more tilted, more eccentric paths. These stars are vertically puffed up, spread farther above and below the galactic plane. And they're chemically different. They're older, formed earlier in the galaxy's history, when there were fewer heavy elements around. They have lower metallicity, less iron, less nickel, less of all the elements, heavier than helium. 3I Atlas's trajectory suggests it might have come from the thick disk. If that's true, if this comet formed in that ancient population, then it could be older than our solar system. Our solar system is 4.6 billion years old.
Thick disk stars can be 7 billion years old or more. That means Sky Atlas could be carrying ice and rock from a time before the sun even existed. Think about what that means chemically.
The gas cloud that collapsed to form a thick disk star 7 billion years ago had fewer heavy elements than the cloud that formed our sun. Supernova explosions enrich the galaxy over time, seeding it with elements heavier than helium. The earliest generations of stars had almost pure hydrogen and helium. Later generations, like our sun, have a few percent of heavy elements mixed in. Stars in the thick disk are intermediate. They have some heavy elements, but less than we do. If 3I Atlas formed in that environment, its composition would reflect that lower metallicity. There would be less iron, less magnesium, less silicon, all the rocky elements that build planets. But there would still be plenty of volatiles. Carbon, nitrogen, oxygen locked into ices and molecules. Maybe that's why we're seeing such a high carbon dioxide to water ratio. Maybe that's why the metal ratios look weird. Maybe this comet is a chemical fossil from a time when the galaxy was younger and the periodic table was emptier. Of course, we can't be sure. Tracing an object back through billions of years of galactic motion is hard. Gravitational perturbations from passing stars, interactions with the galactic spiral arms, encounters with molecular clouds, all of that muddles the trail. The calculations involve uncertainties, assumptions, probabilities, but the fact that it's even plausible that 3I Atlas is older than our solar system is extraordinary. We might be looking at a relic, a survivor, a time capsule from the ancient galaxy. Imagine the story this comet could tell if we could decode its chemistry completely. It formed in a protoplanetary disk orbiting a star we'll never see. That disk collapsed into planets maybe. Or maybe it dispersed without ever forming worlds, scattering comets and asteroids into interstellar space. 3I Atlas was ejected, flung out by gravitational interactions perhaps during the chaotic early days when giant planets were still migrating, still throwing their weight around. Or maybe later, after the system stabilized, a passing star perturbed orbits and kicked this comet loose. For billions of years it drifted, through the cold, through the radiation, through the vast empty spaces between stars. It crossed through the galactic plane, rose up into the thick disk, fell back down. It witnessed the galaxy evolve, stars being born and dying, supernova explosions enriching the interstellar medium, new generations of stars forming from gas clouds seeded with the debris of dead suns. And then by chance, pure statistical chance, its path intersected ours. It fell into our solar system. Gravity bent its trajectory. The sun's warmth began to wake it from its ancient sleep. And we were here, with telescopes pointed at the sky, ready to see it. If we could pinpoint its birth cluster, the group of stars that formed together from the same gas cloud, we might someday identify siblings. Other comets, maybe even planets, ejected from the same system now scattered across the galaxy. 3I Atlas might be one letter in a message written across thousands of light years. And we're just starting to learn how to read it. The comet carries the ashes of stars that died before our sun was even born. It carries water that froze solid when the galaxy was young. It carries chemistry from an era we can only imagine. And for a brief moment, cosmically speaking, it's passing through our neighborhood, giving us a glimpse of deep time, of galactic history, of the vast ancient universe that existed before Earth, before humanity, before any of this. We are small, our lives are brief, but through telescopes and mathematics and stubborn curiosity, we can reach across eons and touch something that should be unreachable. That's what 3I Atlas offers us. Not just a scientific puzzle, but a connection to the deep past. A reminder that we're part of a story much larger and older than ourselves. We've talked about the water, the nickel, the strange behavior at impossible distances. But there's another layer to this mystery that's equally perplexing. 3I Atlas has an inverted chemistry.
Observations suggest that this comet has an extraordinarily high carbon dioxide to water ratio. In our solar system comets, water usually dominates. It's the main volatile, the primary driver of activity. When comets approach the sun and start outgassing water ice, is what's doing most of the work. Carbon dioxide is there, sure, but as a supporting player. Maybe 10% of the volatile budget, maybe 20% in an unusual comet. But water is the star of the show. 3i Atlas flips that script. Some measurements suggest that 95% of the volatile emissions are carbon dioxide with water, as the minority component at only 5%. That's backward. That's inverted. That's nothing like what we see at home. Why would a comet be so carbon dioxide rich? One possibility involves formation temperature.
Carbon dioxide ice condenses at higher temperatures than water ice. In a protoplanetary disk, there's a temperature gradient. Close to the star, it's too hot for any ices to condense. Farther out, it cools down enough for carbon dioxide to freeze. Even farther out, water ice can condense. If 3i Atlas formed in a warmer region of its protoplanetary disk, closer to its parent star than where our comets formed, it might have preferentially incorporated carbon dioxide while losing some of its water. The water might have stayed gaseous at those temperatures, escaping into space, while carbon dioxide locked into solid ice. Or maybe the parent star's radiation field was different. Different stars emit different spectra of light. A hot blue star floods its system with ultraviolet radiation. A cool red star emits mostly infrared. That radiation processes ices in different ways. Ultraviolet light can break apart water molecules, but might leave carbon dioxide relatively intact under certain conditions. Over millions of years of irradiation during the disk phase, the balance of volatiles could shift. Or maybe the giant planets in that system, if there were any, migrated differently. In our solar system, Jupiter and Saturn probably migrated inward and then back outward early in the solar system's history. That migration stirred up the protoplanetary disk, mixing materials from different temperature zones, delivering water-rich comets to the outer solar system. If 3i Atlas's birth system had different migration patterns or no giant planets at all, the mixing might have been different. The comets might have formed in place, never experiencing the compositional averaging that our comets went through. Then there's the cyanide. Cyanide CN is common in comets. It's the molecule that gives many comets their green color, the same green we're seeing in 3i Atlas. But in this comet, the cyanide appeared later in the warming sequence after the water had already turned on. In our comets, cyanide and water tend to show up around the same time because they have similar sublimation temperatures. They're often frozen together, mixed in the ice. When one sublimates, so does the other. The delayed appearance of cyanide in 3i Atlas suggests it might be sequestered differently. Maybe it's trapped in organic molecules that need extra energy to break down. Complex organic molecules can cage small molecules like cyanide inside their structures. As the comet warms and those organic molecules break apart, the cyanide is released. Or maybe the cyanide is frozen in layers beneath the water ice. Picture the comet as a layered structure. The outer layer is mostly water ice. Below that, a layer rich in cyanide and other carbon-bearing molecules. As the comet warms and the outer water layer sublimates away, the cyanide layer gets exposed and starts contributing to the coma. Every element, every molecule we detect is a clue. Volatiles tell us about temperature and pressure during formation. If you know what ices are present and in what ratios, you can work backward to estimate the conditions in the protoplanetary disk. Refractory materials. The stuff that doesn't sublimate easily tells us about condensation sequences and thermal processing. The ratio of gas to dust tells us about the comet's structure and how easily it breaks apart. 3i Atlas is speaking to us in this chemical language. Every spectral line is a word. Every emission feature is a sentence, and we're learning to read it slowly, carefully, testing our translations against models and observations. But here's what's haunting about this particular mystery. If 3I Atlas's chemistry is inverted, if carbon dioxide dominates and water is secondary, then what does that tell us about the frequency of habitable worlds in that kind of system? Water is essential for life as we know it. It's the solvent in which biochemistry happens. Every living thing on Earth is mostly water. Our cells are bags of water with chemistry happening inside. When we search for life elsewhere, we search for water. If planetary systems can form comets that are mostly carbon dioxide, does that mean those systems are poor in water? Does it mean planets in those systems are dry? Or does it mean the water went somewhere else, into planets instead of comets? This is speculation, but it's worth considering. Maybe systems like the one that birthed 3I Atlas are common. Maybe most exoplanetary systems have carbon dioxide-rich comets and water-rich planets, with the two populations having formed in different regions of the protoplanetary disk. Maybe the water stayed closer to the star incorporated into terrestrial worlds, while the carbon dioxide got kicked out to the comet reservoir. Or maybe such systems are poor in water overall. Maybe they're dry systems where planets form without oceans, where life as we know it couldn't take hold. We don't know yet, but every interstellar comet we catalog adds a data point. And with enough data points, we start to understand the diversity of planetary system chemistries. We start to map which kinds of systems are common and which are rare. We start to estimate what fraction of the galaxy's star systems might host habitable worlds. 3I Atlas is one data point, one sample of one, but it's a start. The inverted chemistry tells a story about a place that wasn't like here, about conditions that favored one molecule over another, about a disk that spun and froze and scattered its contents across light years. And now, billions of years later, one fragment of that disk is passing through our solar system, carrying its strange chemistry, its ancient ice, its cosmic message. We're listening, we're analyzing, we're learning what we can while we can before this wanderer moves on and disappears back into the dark between stars.
Let's pause for a moment. Let's step back from the spectroscopy and the orbital mechanics and ask a different kind of question. Why do we care so much about this comet? Yes, it's scientifically interesting. Yes, it's anomalous. Yes, it challenges our models and forces us to think harder about planetary system chemistry. But there's something else happening here, something deeper, more human. We see ourselves in this mystery. Think about it. 3I Atlas is a wanderer. It left home billions of years ago, if it ever had a home, and has been drifting through the galaxy ever since. Alone, cold, silent. For billions of years it experienced nothing but the void, the radiation, the slow tick of cosmic time. And then it woke up. As it approached, our sun warmth found it again. Chemistry reawakened. Volatiles that had been frozen solid for eons started flowing again. The comet began to glow, to exhale, to express itself in wavelengths of light. That's a powerful metaphor for the human condition. How many of us feel like we're drifting, moving through life in a kind of dormant state, frozen, waiting for something to awaken us? And then something happens, a person, an idea, an experience, and suddenly we're alive again, expressing ourselves, feeling things we'd forgotten we could feel. 3I Atlas is a mirror. In its green glow, we see reflected our own journeys through cold spaces and sudden awakenings. But there's more to this than metaphor. Human beings have a deep, almost primal need for mystery. We crave the unknown. We're drawn to puzzles, to questions, without easy answers, to phenomena that defy our expectations. And in the modern world, mystery is increasingly rare. We live in an age of algorithmic predictability. Netflix knows what we want to watch before we do. Google auto-completes our thoughts. Social media feeds us exactly the content we're most likely to engage with. Even our romantic partners are chosen by swiping through algorithmically curated profiles. Life feels increasingly determined, mapped out, predictable, and so we look up. We look to the cosmos for the mystery we've lost down here. We search the sky for the unpredictable, the unexplained, the anomalous.
for things that don't fit neatly into categories, for questions that don't have answers yet. 3i Atlas provides that. It's genuinely strange. Its behavior doesn't match our models. Every observation raises new questions. It refuses to be predictable, refuses to be boring, refuses to fit into the boxes we've prepared for it. And we love it for that. There's a historical parallel here worth noting. In 1910, Halley's Comet returned to the inner solar system. Astronomers had detected cyanogen, a toxic gas related to cyanide in the comet's tail. Newspapers ran sensational headlines, "Comet's poisonous tail will pass over Earth." People were terrified. They bought gas masks. Some sealed their windows with tape and wet towels. There were reports of suicides by people convinced the comet would kill them. Entrepreneurs sold comet pills that would supposedly protect you from the poison gas. Of course, nothing happened. The comet's tail is incredibly diffuse, basically a hard vacuum by terrestrial standards. The amount of cyanogen that actually reached Earth was negligible, undetectable. The comet posed no threat whatsoever, but the panic was real, because comets have always been symbols. They've always meant something beyond their physical reality. For ancient cultures, comets were omens. Their appearance signaled the birth or death of kings, the rise or fall of empires, the favor or wrath of gods. They were messages from the divine written across the sky in fire and ice. We like to think we're past that now. We're scientific. We're rational. We understand that comets are just chunks of ice and rock governed by physics and chemistry. But we're not entirely past it, are we? Look at the social media discussions around 3i Atlas. People connecting it to other astronomical events happening at the same time, seeing patterns, wondering if there's a deeper meaning, asking if the timing is significant. We've replaced gods with aliens, but the impulse is the same. The need to find meaning in cosmic events. The desire to believe that the universe is sending us messages. And maybe, in a way, it is. Not messages in the sense of intentional communication. The universe isn't conscious, probably. It's not trying to tell us anything, but it is revealing things. Every observation, every anomaly, every mystery solved or deepened is a revelation about how reality works, about what's possible, about the nature of matter and energy and time. In that sense, yes, the universe is speaking. And 3i Atlas is part of that conversation. The great psychologist Carl Jung talked about this.
He distinguished between looking outward and looking inward. Who looks outside dreams, he wrote. Who looks inside awakens. When we look at 3i Atlas, we're dreaming outward. We're projecting our hopes and fears and curiosities onto this cosmic wanderer. We're seeing in its behavior a reflection of our own struggles with understanding, with meaning, with our place in the vastness. But maybe, just maybe, the act of looking outward helps us awaken inward. When we confront something genuinely strange, something that doesn't fit our categories, it forces us to question our assumptions, to admit what we don't know, to sit with uncertainty, and that's uncomfortable. Modern life conditions us to always have answers, to always be certain, to never admit ignorance. But science demands the opposite. Science requires us to say, "I don't know," and then figure out how to find out. 3i Atlas is teaching us humility. It's reminding us that the universe is under no obligation to make sense to us, that our models are approximations, not ultimate truths, that reality is always more complex, more surprising, more interesting than we imagine. And in that reminder, there's something beautiful, something almost spiritual if we're willing to use that word carefully. We are not the center of the universe. We are not the culmination of cosmic history. We are brief local phenomena, interesting perhaps, but not privileged. And that's okay. In fact, it's liberating, because it means the universe is bigger than us. It means there are mysteries we haven't solved, places we haven't been, phenomena we haven't witnessed. It means the story isn't over. The cosmos still has things to show us. 3i Atlas is one of those things. A visitor from elsewhere carrying chemistry from elsewhere, showing us that our little corner of the galaxy isn't the whole story. We look up not to know, but to feel again.
To feel wonder, to feel small in the best possible way, to feel connected to something vast and ancient and ongoing. And in that feeling, we find meaning. Not the meaning written in ancient prophecies or divine revelations, but meaning we create through the act of paying attention, of caring, of asking questions. The comet doesn't care that we're watching. It's not performing for us. It's just doing what physics and chemistry dictate. But we care. We care that it's here. We care what its chemistry means. We care about the story it's telling. And in that caring, we become fully human. Curious, wondering, reaching out to touch the cosmos with our minds and our instruments, and our stubborn, beautiful refusal to accept ignorance as final. Now let's roll up our sleeves and dig into the science. Let's examine the most likely explanations for what we're seeing. These are the natural processes, the chemistry and physics, that could account for 3I Atlas's strange behavior without invoking anything exotic or speculative. This is where we spend most of our time because this is where the evidence points. This is the 60% core of scientific explanation. The organometallic hypothesis. Let's start with that nickel anomaly because it's one of the most striking features of this comet. On Earth, in industrial chemistry labs, we work with compounds called nickel carbonyls. The most common is NiCO4 nickel atom bonded to 4 carbon monoxide molecules. This compound is volatile. It forms at relatively low temperatures and pressures, and it sublimates easily. We actually use this in industrial refining. It's part of the Mond process for purifying nickel. You react impure nickel with carbon monoxide gas, forming nickel carbonyl, which vaporizes. Then you heat it, decomposing the carbonyl and depositing pure nickel. Now imagine this process happening naturally in a protoplanetary disk. If the disk, where 3I Atlas formed, was rich in carbon monoxide and many protoplanetary disks are then nickel atoms, could have bonded with CO molecules during the disk's cooling phase. The nickel gets incorporated into volatile compounds. Meanwhile, iron, which doesn't form similar volatile carbonyls, as easily gets locked into refractory minerals. Fast forward billions of years. The comet is approaching the sun. Solar radiation starts warming the surface. The nickel carbonyl compounds reach their sublimation temperature and start breaking down, releasing atomic nickel into the coma. The nickel emits strongly in the green part of the spectrum, creating the glow we observe. But the iron remains trapped in solid grains that need much higher temperatures to vaporize. So we see nickel without iron, not because iron is absent, but because it's sequestered in a form that doesn't sublimate at these relatively low temperatures. This explanation requires specific formation conditions, but nothing impossible. Just a carbon monoxide-rich environment and the right temperature and pressure for these organometallic compounds to form. We can test this hypothesis. As 3I Atlas gets closer to the sun and heats up more, we should eventually see iron start appearing in the spectrum. If the organometallic hypothesis is correct, there's a temperature threshold beyond which the iron-bearing minerals start to sublimate. We just haven't reached it yet. The selective sublimation model. Another natural explanation involves the different vapor pressures of metal-bearing minerals. Not all minerals sublimate at the same temperature. Some are more volatile than others. This has to do with the strength of the chemical bonds holding them together. If 3I Atlas's composition includes nickel-bearing minerals that are unusually volatile minerals that formed under the specific conditions of its birth environment, then those minerals would sublimate first as the comet warms. Iron-bearing minerals with higher sublimation temperatures would remain solid. Think of it like a layered evaporation process. You're not seeing all the metals at once. You're seeing them in sequence, starting with the most volatile and progressing toward the more refractory as the comet heats up. This would create the appearance of nickel without iron, even though both are present in the comet's bulk composition. It's a matter of timing and temperature thresholds. Again, this is testable. Continued observations as the comet approaches perihelion will reveal whether iron emission lines appear at some critical distance.
If they do, that supports the selective sublimation model.
The carbon dioxide driver. Now let's tackle that water mystery. How is 3I Atlas releasing 40 kilograms of water per second at 3.5 astronomical units, where water ice should be stable? The answer might be carbon dioxide. Carbon dioxide ice sublimates at a much lower temperature than water ice. At the low pressures of space, CO2 can start turning from solid to gas at temperatures around 150 Kelvin, maybe even lower depending on conditions. Water ice, on the other hand, needs temperatures closer to 200 Kelvin before it starts sublimating significantly. If 3I Atlas is 95% carbon dioxide ice, as the measurements suggest, then, as the comet approaches the sun, the CO2 starts sublimating first. This happens at great distances far beyond where water would normally be active. But here's the key. As the carbon dioxide sublimates, it drags water with it. Imagine the comet's structure. It's not a uniform ice cube. It's a mixture grains of water ice embedded in a matrix of carbon dioxide ice, all mixed with dust and rock. As the CO2 sublimates, it creates gas pressure beneath the surface. That pressure fractures the ice-lifting chunks of material off the nucleus. Some of those chunks are water ice. They get carried into the coma by the escaping CO2 gas. Once in the coma, exposed to direct sunlight, those water ice grains warm up and start sublimating, even though they're at distances where water shouldn't be active under normal circumstances. It's not that water is sublimating directly from the nucleus at 3.5 AU. It's that carbon dioxide is doing the heavy lifting, excavating water ice and exposing it to conditions where it can sublimate. This is called entrainment in the technical literature. One volatile entrains another, carrying it along. We see this sometimes in our solar system comets, though never to this extreme degree.
If this model is correct, then the ratio of CO2 to H2O emission should change as the comet warms. Close to the sun, at perihelion, water might start sublimating directly from the nucleus, becoming more dominant in the coma. The ratio should shift. We'll know when we get there. The protoplanetary disk temperature gradient. Why would a comet be 95% carbon dioxide in the first place? Our comets aren't like that. What makes 3I Atlas different? The answer probably lies in where it formed within its protoplanetary disk. Every protoplanetary disk has a temperature gradient. Close to the star, it's hot hundreds or thousands of Kelvin. Too hot for any ices to condense. As you move outward, temperature drops. Eventually, you reach what we call snow lines, distances where different volatile species can condense into solid ice. The CO2 snow line is closer to the star than the H2O snow line. This means in a given disk, there's a region where carbon dioxide can freeze, but water cannot.
If 3I Atlas formed in that region, it would preferentially incorporate carbon dioxide, while water remained gaseous and escaped. Alternatively, if the parent star was particularly hot or luminous, its radiation field might have processed the disk differently. Ultraviolet light can photodissociate water molecules, tear them apart, while leaving CO2 relatively intact under certain conditions. Over the millions of years it takes for a protoplanetary disk to form comets, this differential processing could lead to a population of comets that are CO2 dominant. Our solar system didn't produce comets like this because our disk's temperature structure was different. Our comets formed in a region where water ice was stable and abundant, but other systems with different stars and different disk structures would produce different populations of comets. 3I Atlas is showing us one of those alternate outcomes, a comet from a system where the conditions favored carbon dioxide over water. Not a violation of physics, just a different set of initial conditions leading to a different result. These natural explanations, organometallic compounds, selective sublimation, CO2 entrainment, disk, temperature variations account for everything we're seeing without invoking anything exotic. They require only chemistry and physics we already know, applied to conditions that are unusual but not impossible. This is where responsible science lives.
in the space between what we observe and what we can explain with established principles. Stretching those principles to new conditions, yes, but not breaking them. And that's beautiful in its own right, because what it's telling us is that the universe is more diverse than we experienced. That our solar system, for all its wonders, is just one example of what's possible. That comets can come in varieties we never imagined, shaped by environments we've never directly observed. 3I Atlas is weird, but it's probably naturally weird. Exotic circumstances producing exotic outcomes. And that's extraordinary enough.
Now let's venture into slightly stranger territory. These hypotheses are still natural, no alien intervention, no new physics, but they invoke processes that are rare or poorly understood. These are the edge cases. The unusual but not impossible scenarios. This is our 25% of speculation, the zone where science gets creative while staying grounded. Pre-solar chemical inheritance. Remember that thick disk origin we discussed earlier? That idea that 3I Atlas might come from a population of stars that formed 7 billion years ago or more before our sun existed. If that's true, the chemical implications are profound. The galaxy's metallicity, the abundance of elements heavier than helium, has been increasing over time. Early generations of stars formed from nearly pure hydrogen and helium. When those stars died, especially the massive ones that exploded as supernovae, they seeded the interstellar medium with heavy elements.
Carbon, nitrogen, oxygen, silicon, magnesium, iron. All the elements that build planets and life. The next generation of stars formed from gas clouds enriched by those supernova explosions. And the next generation was even more enriched. And so on. Stars in the thick disk formed during an intermediate stage of this process. They have more heavy elements than the earliest stars, but less than our sun. If 3I Atlas formed in a thick disk star system, its chemistry would reflect that lower metallicity. But here's where it gets interesting. Different types of supernova produce different ratios of elements. Type Ia supernovae exploding. White dwarfs produce lots of iron and nickel in fairly consistent ratios. Core collapse supernovae, massive stars exploding at the end of their lives, produce different ratios depending on the star's mass and composition. If 3I Atlas's parent system formed from gas enriched primarily by one type of supernova over another, its bulk composition could have unusual elemental ratios. Maybe the gas cloud that formed its parent star was enriched by supernova that produced more nickel relative to iron than typical. Maybe it formed in a region of the galaxy that experienced an unusual supernova rate or type distribution. The nickel anomaly we're seeing could be a fossil signature of that ancient chemical environment. A fingerprint left by long-dead stars preserved in ice for billions of years, now revealed as the comet sublimates. This is speculation, but it's grounded in what we know about galactic chemical evolution. It's testable too if we could measure the comet's isotopic ratios precisely. Different supernova types produce different isotopic signatures, different ratios of, say, nickel-58 to nickel-60. Those ratios would tell us about the nuclear processes that created the comet's metals. Unfortunately, getting those measurements from Earth-based spectroscopy is extremely difficult. We'd probably need a sample return mission, but the hypothesis is there waiting to be tested. The radiation processing hypothesis. Here's another edge case. What if billions of years of cosmic radiation bombardment altered 3I Atlas's surface chemistry in ways we don't fully understand? Interstellar space is not empty. It's filled with cosmic rays, high-energy particles, mostly protons traveling at near light speed. These particles slam into any object in their path, penetrating deep into surfaces, breaking chemical bonds, creating new compounds. Ultraviolet radiation from distant stars does similar work, photodissociating molecules, creating radicals driving chemistry that wouldn't happen thermally. Over billions of years, this radiation processing can create a space weathering rind on comets and asteroids.
the surface chemistry becomes different from the interior. We see this on lunar rocks and on meteorite surfaces darkened and chemically altered by long exposure to space. Maybe 3I Atlas's nickel signature comes from this weathering rind. Perhaps radiation processing preferentially mobilized nickel into volatile compounds at the surface while leaving iron locked in minerals beneath. When the comet approaches the sun and the surface starts sublimating, we see the nickel-enriched weathering products, not the bulk composition. This would mean the nickel without iron is real but misleading. It's telling us about surface processing, not about the comet's formation chemistry. As the comet continues to sublimate, as more material is removed from the surface, we might eventually break through that weathering rind and start seeing the true bulk composition, which might include more iron. Again, testable. Keep watching, keep measuring. The thermal remnant hypothesis. Here's a wild one. What if 3I Atlas is still warm from its formation? Comets form cold. They're made of ice. Surely they're frozen all the way through, right? Usually, yes, but there are scenarios where a comet could retain internal heat for billions of years. One is radiogenic heating. If the comet contains enough long-lived radioactive isotopes, potassium-40, thorium-232, uranium-238, the decay of those isotopes releases heat. Over billions of years, that heat can keep the interior warmer than you'd expect. In our solar system's comets, this heat is negligible. There's not enough radioactive material to matter. But if 3I Atlas formed in an environment with higher abundances of these isotopes, if its parent system's chemistry was different, then radiogenic heating might be significant. Another possibility is that the comet had a catastrophic event in its past, maybe a collision with another object 1,000,000 years ago. Such an impact would have released enormous energy heating the interior. If the comet is large enough and well insulated enough, that heat could persist for a long time. Warm interiors would explain the distant activity. If there's warmth below the surface that could drive sublimation even when surface temperatures are too low. Volatiles could be migrating from the warm interior to the cold surface, finding paths through cracks and pores, and escaping. This is speculative. We have no direct evidence of internal temperatures, but it's not impossible. It's an edge case worth considering. The unknown ice hypothesis. Finally, let's consider the possibility that 3I Atlas contains ices we're not familiar with. We know about water ice, carbon dioxide ice, carbon monoxide ice, methane, ice, ammonia ice. These are the common volatiles, the ones we see in our solar system and expect elsewhere. But the periodic table has lots of elements.
And many combinations of those elements can form ice-like solids at low temperatures. What if 3I Atlas contains, say, nitrogen compounds we've never encountered, complex organics that sublimate at unusual temperatures, Clathrates cage structures where one molecule is trapped inside a lattice of another with properties we haven't studied. Formation in a different chemical environment could produce ices that are thermodynamically stable but rare or absent in our solar system, and those ices could sublimate at temperatures that surprise us, driving activity at distances we didn't predict. This is the most speculative of the unusual natural hypotheses. It's essentially saying there might be chemistry we haven't thought of, which is always true but not particularly useful unless we can specify what that chemistry might be. Still, it's worth keeping in mind the universe is under no obligation to limit itself to the chemistry we've observed, and an interstellar comet from an environment very different from ours might well carry molecules we've never encountered. These unusual natural explanations push the boundaries of what we know. They're less likely than the straightforward natural processes we discussed earlier, but they're still within the realm of possibility. They remind us that science is a process of exploration, not just confirmation. We build models based on what we've seen, but we have to stay open to the possibility that nature has tricks we haven't witnessed yet. 3I Atlas might be showing us one of those tricks. And if it is, that's exciting,
Because it means our understanding expands. Our catalog of possible phenomena grows. Our sense of what the universe can do becomes richer. That's how science progresses. Not just by confirming what we already believe, but by encountering things that don't quite fit, and then figuring out why. All right, now we enter speculative territory. These are the what-if scenarios, the bold possibilities that capture imagination but rest on thin evidence. This is our 15% speculation budget, and we're going to use it carefully with clear caveats. These ideas are not likely to be true. They're thought experiments, but they're worth exploring because sometimes the improbable turns out to be correct, and because thinking through these scenarios helps us understand what evidence would actually prove them. So let's be clear, what follows is speculation. Fascinating speculation perhaps, but speculation nonetheless. The panspermia vector 3I Atlas has water. It has organics. It has cyanide, which is a key precursor in prebiotic chemistry, the chemistry that leads to life. If you wanted to design a comet to seed a planet with interesting chemistry, you'd include exactly these ingredients. The panspermia hypothesis suggests that life, or at least life's building blocks, can spread through space on comets and asteroids. A comet impacts a planet delivering organic molecules. Those molecules get incorporated into the planet's chemistry. Eventually, under the right conditions, life emerges. It's an old idea. The Greek philosopher Anaxagoras proposed something similar in the 5th century BCE. In modern form, scientists like Svante Arrhenius and Fred Hoyle championed it. More recently, astrobiologists have explored it seriously. The chemistry checks out. Comets do carry organic molecules. We've detected amino acids in meteorites that originated in asteroids. Complex organics can form in space and survive delivery to planetary surfaces. But there are serious problems with panspermia. First, cosmic radiation is brutal. High-energy particles tear apart complex molecules. Over millions of years in interstellar space, DNA proteins, even simple amino acids, can be destroyed. For life to survive an interstellar journey, it would need to be buried deep inside the comet, shielded by meters of ice and rock. Second, the heat of atmospheric entry is intense. When a comet hits a planet at tens of kilometers per second, the energy released is enormous. Temperatures soar. Most organic material would be incinerated. That said, not all of it would be. Material from the comet's interior, protected by the outer layers that ablate away, might survive. We found amino acids in meteorites after all, and those meteorites experienced atmospheric entry. So could 3I Atlas be carrying the building blocks of life? Maybe. The ingredients are there. But to be clear, we're not talking about living organisms. We're talking about complex molecules. Amino acids, perhaps. Nucleobases, maybe. The chemical precursors that, in the right environment, could lead to life. These molecules wouldn't be alive themselves. They'd be fossils of sorts. Chemical fossils. Molecules that were synthesized somewhere, maybe in the parent star's protoplanetary disk, maybe in a planet's atmosphere, maybe in an ocean, and then got incorporated into the comet during its formation. If we could analyze 3I Atlas's organic inventory in detail, if we could identify specific molecules and measure their properties, we might learn things about prebiotic chemistry that we can't learn any other way. We might discover metabolic pathways we hadn't imagined. We might find molecules that suggest different biochemical possibilities. We might get hints about whether the building blocks of life are common in the galaxy or rare. But let's be intellectually honest here. There's no evidence that 3I Atlas is carrying life or even unusual organic molecules. The cyanide we've detected is common. The water is ordinary. Nothing we've seen so far screams biology. This is speculation. It's a thought experiment about what's possible, not a claim about what's probable. The industrial contamination signature. Here's an even wilder idea. Brace yourself. What if 3I Atlas's unusual metal ratios aren't natural at all? What if their technosignatures evidence of industrial processing by an advanced civilization? Let me immediately say there is no evidence for this. None. This is fringe speculation. But let's explore it anyway because it illustrates what kinds of signatures we might look for if we were serious about detecting technological activity in space. Industrial processes are selective. When humans refine metals, we extract what we want and discard the rest. Iron gets pulled out for construction. Nickel gets used for specific alloys. The waste products have anomalous elemental ratios because the natural ratios have been artificially altered. If an advanced civilization were mining asteroids, refining metals, building structures in space, they'd generate waste. Slag tailings exhaust. That material would drift through the system. Some of it might get incorporated into comets forming in the outer reaches. Millions or billions of years later, that comet gets ejected, wanders the galaxy, and arrives here. We detect the nickel anomaly and assume it's natural. But maybe it's not. Maybe it's the faint signature of industrial activity from a civilization that might not even exist anymore. To be absolutely clear, this is extraordinarily unlikely. The natural explanations we discussed earlier, organometallic compounds, selective sublimation, pre-solar chemistry, are far more probable. They require only processes we know happen applied to unusual but not impossible conditions. The industrial hypothesis requires an advanced civilization, asteroid mining, waste incorporation into comets, and the comet surviving billions of years of interstellar travel. That's a lot of assumptions stacked on top of each other, but it's not physically impossible. And here's the thing, if we ever do encounter an artificial interstellar object, it might not look obviously artificial at first. It might look like a comet. A weird comet, sure, but explicable as natural until you dig deeper. 3I Atlas isn't that. Almost certainly isn't that, but the fact that we're even asking the question tells you how strange its behavior is. The exotic physics wildcard. Finally, let's consider the possibility that 3I Atlas is revealing processes we genuinely don't understand yet. Not alien technology, not biology, just physics and chemistry operating under conditions or in ways we haven't encountered. Maybe there are sublimation mechanisms we don't know about. Maybe quantum tunneling effects become significant in certain crystal structures at low temperatures, allowing molecules to escape even when classical thermodynamics says they should be stable. Maybe there are catalytic processes happening on the comet's surface driven by cosmic rays or solar wind that break down minerals in unexpected ways. Maybe the interaction between ice and organic material creates emergent properties, complex system behaviors that arise from simple components interacting in non-obvious ways. We're constantly discovering new physics, not violations of known laws, but phenomena that occur in parameter spaces we haven't explored. Ultra-cold atoms exhibit quantum behaviors we couldn't have predicted. Complex systems show emergent properties that aren't obvious from their components. 3I Atlas might be operating in one of those unexplored spaces, a regime where our models are incomplete, not because they're wrong, but because they haven't been tested under these specific conditions. If that's the case, then studying this comet will expand our understanding. We'll learn something genuinely new about how matter behaves. And that's exciting even if it's not revolutionary. The takeaway from all these speculative scenarios is this: science requires imagination, but imagination must be disciplined by evidence. It's okay to speculate. It's good to ask, what if, and explore unlikely scenarios. That's how we identify what evidence we'd need to confirm or rule out those scenarios. But speculation must be clearly labeled. We must distinguish between what we know, what we suspect, and what we're imagining. 3I Atlas is probably a natural comet with unusual but explicable chemistry. It probably formed in conditions different from our solar system, and it's showing us behaviors we haven't seen before because we're observing chemistry from a different environment. That's the most likely explanation. That's where the evidence points. But could it be something more? Could it be carrying prebiotic chemistry or industrial signatures or exotic physics? Possible, yes, in the sense that these things don't violate known laws. Probable, no. The evidence doesn't support them, and that distinction between possible and probable is crucial. It's the difference between responsible science and wild speculation. 3i Atlas is extraordinary. B. Sometimes the most important discoveries happen because someone was looking at the data in just the right way. Not with algorithms, not with machine learning, but with human eyes and human intuition. And sometimes that someone isn't a professional astronomer at all. Let me tell you about odd radio circles. If you haven't heard of them, you're not alone. They were only discovered in 2019, which, in astronomy terms, makes them practically brand new. Odd radio circles, ORCs for short, are vast circular structures visible only in radio wavelengths. You can't see them in optical light. You can't see them in infrared. Point a radio telescope at the right patch of sky, and there they are. Perfect rings of radio emission, sometimes hundreds of thousands of light years across, floating in space like cosmic smoke rings. Nobody knows what they are. The leading theory involves galactic winds or shock waves from supermassive black holes, but honestly, we're still figuring it out. They're genuinely mysterious, and finding them is hard because they're faint and they blend into the radio background. Automated detection algorithms tend to miss them because they're trained to find point sources or compact objects, not large diffuse rings. Enter Radio eHome. This is a citizen science project where volunteers visually inspect radio continuum maps looking for things that don't fit. They're not looking for anything specific. They're looking for weird, for anything that makes them pause and think, that's odd. In March 2025, a volunteer flagged something extraordinary. The object is catalogued as J1313+52. It's a pair of intersecting radio rings, twin circles overlapping in the sky, creating a figure-8 pattern. It's the most distant and most powerful ORC discovered so far. And it was found not by an algorithm, not by a professional survey, but by someone volunteering their time to stare at data.
The discovery was made using low-frequency continuum maps from LOFAR, the Low-Frequency Array, a radio telescope network spread across Europe. LOFAR generates enormous amounts of data, too much for professional astronomers to examine by hand. Automated pipelines process most of it, flagging candidate objects based on brightness, shape, and other parameters. But those pipelines have filters. They have thresholds. They're designed to catch the expected, not the unexpected. This is where human pattern recognition becomes invaluable. Our brains are incredible at spotting things that don't belong, at seeing structure in noise, at flagging something as interesting even when we can't articulate why. The volunteer who found J1313+50 didn't need to know the physics of ORCs. They just needed to look at the image and think, that's weird. And they were right. But it's not just that one object. Radio eHome has flagged multiple anomalies. Another volunteer found a giant radio galaxy with a peculiar ring structure around it. Another found a ring at the end of a jet, a feature that theoretical models didn't predict. These are objects that would have been lost in the data flood if humans hadn't been looking. There's a lesson here that extends beyond radio astronomy. We're entering an era of data deluge. The Vera Rubin Observatory, when it comes online, will generate 15 terabytes of data every night. 15 terabytes every night for 10 years. No human team can look at all of that. No set of algorithms can catch every anomaly. We need both. We need machines to handle the bulk processing and humans to catch the weird edge cases that don't fit any existing template. Now let's connect this back to 3i Atlas. Could a citizen scientist have flagged its anomalies early? Could someone looking at spectral data have noticed the nickel without iron signature before professional astronomers did? Maybe. Maybe not. Spectroscopy is hard. It requires understanding line identifications, wavelength calibrations, signal-to-noise assessments. It's not something you can do casually, but with training, with guidance, with a community of people working together, it's possible. Amateur astronomers already contribute to comet science. Light curves measurements of brightness over time are often made by amateurs with backyard telescopes. If those amateurs had been looking at ultraviolet data from Swift, if they'd been trained to recognize unusual activity patterns, they might have flagged 3I Atlas's superlinear brightening early. They might have said, "This doesn't look like a normal comet," before professional surveys confirmed it. The history of astronomy is full of amateur discoveries. The Japanese amateur astronomer Kaoru Ikeya discovered multiple comets visually just by knowing the sky well enough to notice when something new appeared.
The British amateur Andrew Gray co-discovered an unusual stellar outburst. These aren't flukes. They're examples of what happens when passionate people with telescopes or access to data decide to look carefully at the universe. In the future, as telescopes flood us with petabytes of data, citizen scientists might become the first responders to cosmic oddities. They might be the ones who flag the next interstellar comet, the next weird radio structure, the next thing that doesn't make sense. And when they do, professional astronomers will follow up, investigate, figure out the physics. It's a partnership, and like all good partnerships, it's stronger than either component alone. But let's not pretend this is all sunshine and collaboration. There's tension here. Real tension. Opening the gates to citizen science means dealing with false positives, with well-meaning amateurs who flag things that turn out to be artifacts or noise, with conspiracy theorists who see alien signals in every data glitch. Professional astronomers understandably worry about this. The Royal Astronomical Society and other professional bodies have debated it extensively. On one hand, citizen science reduces the backlog. It allows projects to process more data than would otherwise be possible. It engages the public and creates enthusiasm for science. On the other hand, quality control is essential. A discovery isn't a discovery until it's been verified, cross-checked, and peer-reviewed. And that takes time and expertise. False positives are a real problem. Someone flags an object as unusual. Astronomers spend days or weeks following up only to determine its instrumental noise or a satellite trail or a cosmic ray hit. That's time that could have been spent on genuine discoveries. And when false positives pile up, astronomers become skeptical of citizen reports. The signal-to-noise ratio drops. Fatigue sets in. But these problems aren't insurmountable. They're challenges, not deal-breakers. Training protocols can help. If citizen scientists are taught how to assess data quality, how to recognize artifacts, how to estimate uncertainty, the false positive rate drops. Tiered validation systems help too. Require multiple independent volunteers to flag the same object before it's elevated for professional follow-up. That filters out spurious detections, and the opportunities are enormous. Crowdsourcing anomaly hunts means you can search larger datasets more thoroughly. Cross-checking by many independent eyes reduces the chance that a real anomaly gets missed because one person was having an off day. Diverse perspectives mean people from different backgrounds might notice patterns that specialists overlook. The conclusion isn't that we should replace professional astronomers with amateurs. That's absurd. The conclusion is that we need both. We need professionals for the deep expertise, the theoretical frameworks, the rigorous validation. And we need citizen scientists for the breadth of coverage, the fresh perspectives, the sheer number of eyes. It's not a competition, it's a partnership. And in the era of data deluge, it's a necessary partnership. 3I Atlas is being studied by professionals with the best instruments and the deepest expertise. But the next interstellar visitor might be flagged by an amateur astronomer with a backyard telescope and a sharp eye, or by a volunteer scanning data on their laptop at home. When that happens, we'll be glad they were looking, because the universe is vast and we need all the eyes we can get to watch it. October 2025 brought something unusual: excellent viewing conditions for both Mercury and Ceres. Mercury, the innermost planet, swung into a favorable evening apparition, bright and high above the horizon after sunset. The best viewing opportunity in months. Ceres, the largest object in the asteroid belt, reached opposition, meaning it was directly opposite the Sun in the sky at its brightest and closest to Earth. On social media, people started connecting dots. Mercury visible, Ceres visible, and now this weird interstellar Comet 3I Atlas acting alive. Were they related? Was there some cosmic alignment happening? Were the solar system's gravitational fields somehow triggering or amplifying the comet's activity? Let's be clear. No, there is no connection. Mercury's orbit has nothing to do with an interstellar comet's outgassing. Ceres's position relative to Earth has no influence on chemistry happening billions of kilometers away. These are independent events, coincidentally visible at the same time. Nothing more. But people love patterns. We're wired to find them. It's a survival trait. Our ancestors who noticed that certain berries caused sickness and certain animal tracks led to prey were more likely to survive than those who didn't notice patterns. So our brains are hypersensitive to patterns, sometimes to the point of finding them where they don't exist. This is pareidolia on a cosmic scale. Pareidolia is seeing faces in clouds, hearing voices in static. It's pattern detection gone haywire. And it happens with celestial events all the time. Ancient cultures saw omens in planetary alignments. When a comet appeared during a battle, it meant the gods were angry. When planets gathered in one part of the sky, it signaled the birth or death of kings. The year 1910 provides a perfect historical analogy. That's the year Halley's Comet returned, swinging through the inner solar system on its 76-year orbit. Astronomers had detected cyanogen, a toxic gas related to cyanide in the comet's tail. Newspapers ran sensational headlines, "Comet's poisonous tail will pass over Earth." People were terrified. They bought gas masks. Some sealed their windows with tape and wet towels. There were even reports of suicides by people convinced the comet would kill them. Entrepreneurs sold comet pills that would supposedly protect you from the poison gas. Of course, nothing happened. The comet's tail is incredibly diffuse, basically a hard vacuum by terrestrial standards. The amount of cyanogen that actually reached Earth was negligible, undetectable. The comet posed no threat whatsoever, but the panic was real, because the comet's appearance coincided with other unrelated events. Solar activity, political unrest, earthquakes. People connected dots that didn't connect. They saw patterns that weren't there. We're seeing the same thing now with 3I Atlas. The comet is weird, genuinely anomalous. Mercury and Ceres happen to be visible at the same time, and suddenly people are constructing narratives. Maybe the comet is being awakened by some solar system resonance. Maybe its trajectory is being subtly altered by gravitational perturbations. Maybe this is all part of a larger pattern we don't yet understand. Astronomers have run the numbers. The gravitational influence of Mercury on an object in the outer solar system is essentially zero. Mercury is tiny, only slightly larger than our moon, and it's far away. Ceres is even smaller and even less influential. The combined gravitational pull of every planet in the solar system couldn't significantly alter 3I Atlas's behavior at the distances we're observing it. The comet is doing what it's doing because of internal processes, solar radiation, and its own composition. Not because of where Mercury happens to be in its orbit, but facts don't always matter when narratives are compelling. The human brain craves stories. We want events to be connected because disconnected events feel random, chaotic, meaningless. If the comet's activity is linked to planetary positions, then there's order, there's predictability, there's meaning. If they're unrelated, then we live in a universe where strange things just happen sometimes. And that's psychologically uncomfortable. Confirmation bias magnifies this effect. Once you start looking for connections, you find them everywhere. Mercury was also visible during a previous comet discovery. Ceres was near opposition when another unusual object was detected. Never mind that Mercury is visible several times a year. Never mind that Ceres reaches opposition annually. Never mind that unusual astronomical discoveries happen constantly. The brain filters out the non-coincidences and remembers only the ones that fit the narrative. Social media amplifies this exponentially. In the old days, if you had a theory about planetary alignments affecting comets, you might tell your friends who would probably tell you it was nonsense, and that would be the end of it. Now you post your theory online and instantly find a community of people who think the same way. You share links, images, charts showing the alignments. Someone adds a new piece of evidence. Someone else shares it further. Before long, you have a full-blown alternative narrative competing with the scientific explanation. The lesson here isn't that people are stupid or gullible. The lesson is that coincidences are powerful, and our brains aren't well calibrated to dismiss them. Statistically, with thousands of astronomical events happening all the time, some will coincide purely by chance. And those coincidences will feel meaningful even when they're not. This matters because it affects how people interpret anomalies like 3I Atlas. If you're primed to see cosmic conspiracies to believe that alignments matter, then the comet's weird behavior becomes evidence of something larger. Maybe it's not a natural comet at all. Maybe it's artificial. Maybe it's responding to signals from the planets. Maybe it's part of some grand cosmic mechanism we don't understand. And that brings us to an even stranger chapter in this story. The machinery of hoaxes, conspiracy theories, and how humans turn scientific mysteries into cultural myths. But before we go there, let's sit with this thought for a moment. The universe doesn't care about our need for patterns. Events happen independently. Causation and correlation are different things. And just because two things occur at the same time doesn't mean they're related. 3I Atlas is weird on its own merits. It doesn't need Mercury and Ceres to make it interesting. The chemistry is anomalous, regardless of planetary positions. The behavior is unprecedented whether or not other objects are visible in the night sky. The real mystery is the comet itself, not the timing of its discovery, not the celestial configuration when we observed it. The mystery is written in spectral lines and sublimation rates and metal ratios. The mystery is about where this object came from and what its chemistry reveals about planetary system formation in different environments. That's the story worth telling. The coincidences, the alignments, the patterns we imagine we see, those are just noise. Human noise obscuring the real signal. And the real signal is this: the universe is more diverse than we imagined. Comets can form under conditions vastly different from our solar system, and when those comets visit us, they show us things we've never seen. That's extraordinary enough without needing cosmic alignments to make it interesting. October 8, 2025. Blue Origin mission NS-36, 6 passengers, 11 minutes. One mystery flyer whose name stayed secret until wheels down. The capsule launched, crossed the Kármán line, floated in microgravity, descended under parachutes, and touched down in the Texas desert. Success. Another flawless flight, their 15th crewed mission. That's the official story. ABC News covered it. Medium ran a piece. A handful of space journalists tweeted about it. The mystery passenger was revealed post-landing. Nothing unusual there. People pay for privacy all the time. But here's what's strange: the silence. The eerie lack of coverage. No viral videos, no trending hashtags, no celebrity reactions or memes or TikTok breakdowns. A space flight, a commercial crew crossing into the edge of space. Something that just a few years ago would have been headline news for days. Barely registered a blip. 6 human beings left the planet. They experienced weightlessness, saw Earth's curve against black space, and returned safely. That's extraordinary. But the internet shrugged. Social media moved on within hours. Why so little documentation? Blue Origin usually releases cabin footage, passengers floating, laughing, pressing faces against windows. Where were those images? Why didn't the mystery passengers reveal generate curiosity? Who were they? Why did they want anonymity? These are natural questions, the kind that usually fuel days of speculation and interest. Instead, nothing. Radio silence. It's as if the flight happened in a vacuum not just of space but of public attention, and that vacuum starts to feel like its own presence. The silence becomes louder than any announcement could be. You start to wonder, did this flight really happen as described? Were there 6 passengers, or was the manifest different? Was the mystery passenger real or a narrative device to explain the lack of pre-flight publicity? Did the capsule actually launch on October 8th, or was footage from a previous flight repackaged with a new date stamp? These are paranoid thoughts, conspiracy thinking, but sometimes the absence of evidence feels significant. When something should make noise, and doesn't, you have to ask why. Let's contrast this with April 2025. Blue Origin launched another mission with Katy Perry, Gayle King, high-profile passengers. That one exploded into public consciousness. And it did. But not the headlines Blue Origin wanted. Within hours of the live stream ending, social media erupted with conspiracy theories. People claimed the flight was faked. They analyzed every frame of footage looking for inconsistencies. Hair behavior in zero gravity became a forensic battlefield. Does it float right? Does it move too stiffly? Is that real hair or a wig or computer generated? The capsule hatch became another focal point. Someone claimed it opened differently than in previous flights. They posted side-by-side comparisons. Drew arrows circled supposedly anomalous details. Wasn't the latch on the other side last time? Didn't the door swing outward before? Why does this look different? Then came the really wild stuff. Claims of green screens. Allegations that the passengers were filmed in a studio with fake windows showing pre-recorded Earth footage. Accusations that hands looked like mannequin hands, too smooth, too plastic. Complaints about the absence of visible scorch marks on the capsule after re-entry. Every tiny detail became evidence of deception. Journalists debunked the claims methodically. Hair behaves weirdly in microgravity because there's no gravity pulling it down, so it responds to air currents, static electricity, random motion. The hatch mechanism is identical across flights. Camera angles and lighting make it look different. Reflections in visors distort perspective. Scorch marks aren't always visible depending on landing site dust coverage and camera resolution. But debunking didn't stop the theories. If anything, it fueled them. People who wanted to believe the flight was fake interpreted the debunking as cover-up. They dug deeper, found more evidence, built elaborate models of how the hoax was perpetrated. The conspiracy became self-sustaining. Now we have 2 flights, 2 missions, same rocket, same basic profile, 6 months apart. One generated a firestorm of attention and doubt. The other barely made a sound, and you have to ask, which is more suspicious, the flight that everyone saw and questioned, or the flight that nobody seems to have noticed? I'm not suggesting NS-36 didn't happen. The evidence suggests it did. ABC News is a reputable outlet. The handful of space journalists who covered it are credible, but the silence is curious. In an age where everything is documented, where every moment is live-streamed and shared and commented on, a spaceflight passing with minimal fanfare feels almost deliberate. Maybe it's just a slow news cycle. Maybe there were bigger stories that day. Maybe people are becoming desensitized to spaceflight. What was miraculous 5 years ago is now routine. Or maybe there's a lesson here about how we consume information. We're drawn to controversy, to conflict, to things that feel scandalous or questionable. A smooth, successful flight with anonymous passengers doesn't feed that hunger. There's nothing to argue about, nothing to investigate, nothing to amplify, so it gets ignored. Meanwhile, a flight with celebrities generates instant scrutiny because people are watching for something to criticize. They're primed to find problems. This is human nature. This is how our attention works in the social media age, and it has implications for how we process scientific mysteries like 3-Eye Atlas. If the comet's behavior fits expectations, if it's mundane, nobody pays attention. But if it's weird, if there's something anomalous, Suddenly everyone's an expert, everyone has a theory, everyone sees patterns and connections and deeper meanings. The Blue Origin NS-36 mystery, if it's even a mystery, is just the absence of expected noise. The dog that didn't bark, as Sherlock Holmes would say. And maybe that's the real lesson. Sometimes the absence of something expected is worth noticing, but absence isn't evidence. Silence doesn't prove anything, and our discomfort with unanswered questions doesn't mean there's a conspiracy. Maybe NS-36 was just a quiet success. Maybe the passengers valued their privacy. Maybe the media had other priorities, or maybe, just maybe, the silence itself is what we project meaning onto. Another pareidolia pattern.
Another case of humans seeing significance in randomness. The universe doesn't owe us explanations. Neither does a private spaceflight company. Sometimes things just happen or don't happen without deeper meaning. And learning to sit with that uncertainty, learning to distinguish between genuine mysteries and manufactured ones, is part of growing up as a species. 3I Atlas is a genuine mystery. NS-36's silence is probably not. Knowing the difference matters. Imagine the galaxy as a library, not a library of books, but of objects, comets, asteroids, rogue planets ejected during the chaotic formation of planetary systems and flung into interstellar space. Each object is a message in a bottle carrying information about the star system where it formed, and occasionally one of those bottles washes up on our shore. That's what interstellar objects are. Postcards from alien systems. Not alien in the sense of extraterrestrial intelligence. Alien in the sense of foreign, different, formed under conditions unlike those in our solar system. Everyone we detect is a data point, a sample of one, and with enough samples we start to understand the diversity of planetary system chemistries across the galaxy. Our solar system comets are relatively uniform. They formed in the same protoplanetary disk, from the same well-mixed gas and dust, under the same stellar radiation field. They vary, sure. Some are more carbon monoxide rich, some more water rich. It depends on where in the disk they formed and what temperatures they experienced. But they're family, siblings, cousins at most. Interstellar comets are strangers. They formed elsewhere under different stars and disks with different compositions, different temperatures, different dynamical environments. And so far, everyone we've seen has been different. Oumuamua, dry, non-outgassing, oddly shaped, accelerating mysteriously. It didn't look like our comets. It didn't act like our comets. If it was a comet at all, it was a type we'd never encountered. 2I Borisov, carbon monoxide rich. Fairly typical comet behavior, but with a gas-to-dust ratio suggesting a colder formation environment than most of our comets. It looked familiar, but subtly off, like a dialect of a language you speak. 3I Atlas, water and carbon dioxide gushing at great distances. Nickel without iron. Cyanide appearing late. Nothing about its behavior fits our experience. It's speaking a language we barely recognize. 3 objects, 3 wildly different chemistries. If we extrapolate, if we assume these 3 are representative of the broader population, then the diversity of cometary compositions in the galaxy is staggering. Not all planetary systems produce comets like ours. In fact, maybe most don't. Think about what that means. In some systems, comets might be dominated by nitrogen ice like Pluto's surface. In others, methane might be the primary volatile. In systems with more massive stars, the snow line, the distance where water ice can condense, is farther out. So comets might form in colder regions and carry different volatile mixes. In systems with migrating giant planets, the disk gets stirred, mixing materials from different temperature zones, creating comets with weird hybrid compositions. Could some comets carry molecules we've never seen, molecules that are thermodynamically possible but require formation pathways that don't exist in our solar system, exotic organics? Strange ices, compounds that would make a chemist's eyes light up. Probably,
The universe is big. The parameter space of stellar masses, disk, compositions, radiation fields, and dynamical environments is enormous. Nature explores that parameter space thoroughly, and some of the results have to be strange. Now let's take this a step further. If life requires certain chemical building blocks, water, organics, phosphorus, nitrogen, sulfur, then comets, that lack those ingredients are sterile. They can't seed life. They can't deliver prebiotic chemistry to planets. Maybe many interstellar comets are sterile. Maybe Oumuamua was a lifeless rock tumbling through the void. But if even a fraction of comets carry the right chemistry, that fraction is important. Because comets are galactic wanderers. They travel between stars, they cross light years, and if they carry organic molecules, amino acids, maybe even dormant microbes shielded deep inside, then life's building blocks can spread across the galaxy. This is panspermia, the hypothesis that life can be transferred between worlds on comets or asteroids. It's controversial, it's unproven, but it's not impossible. And 3I Atlas, with its water, its organics, its cyanide, has the ingredients. Not life, probably, but the chemistry that could lead to life if delivered to a suitable planet. Every interstellar object we detect expands our sample. Right now, we have 3. In 10 years, we might have dozens. In 50 years, hundreds. And with each one, we'll measure composition, trajectory, activity patterns. We'll build a statistical understanding of what's out there. Maybe we'll find that water-rich comets are common, that most planetary systems produce them. That would suggest the building blocks of life are abundant in the galaxy. Or maybe we'll find that our solar system is the oddball, that water-rich comets are rare, and most systems produce dry, carbon-rich bodies. That would suggest habitable worlds might be rarer than we hope. Either answer is fascinating, and maybe, just maybe, we'll find a comet with clear biomarkers, molecules that are hard to explain without biology, phospholipids, complex organics with chirality, isotope ratios that scream metabolism. That would be revolutionary. That would tell us life arose elsewhere, that biochemistry isn't unique to Earth. We haven't found that yet. 3I Atlas isn't carrying life as far as we can tell, but it's carrying information, and information is the currency of science. Every interstellar visitor is a gift, a free sample delivered to our doorstep. All we have to do is look closely enough. The Vera Rubin Observatory is coming online soon. Estimates suggest it could detect 1 interstellar object per month, maybe more. That's 12 per year minimum. In a decade, over 100 confirmed interstellar visitors. That's a statistical sample. That's enough to start drawing real conclusions about compositions, origins, populations. The Square Kilometre Array, a radio telescope network being built in Australia and South Africa, will also contribute. Radio observations can detect molecular emissions from comets, even faint ones. SKA could spot interstellar comets that optical telescopes miss.
Space-based ultraviolet and infrared telescopes will catch comets that are active but obscured at optical wavelengths. Every new instrument expands our detection capability, our ability to see these faint, fast wanderers. But detecting is one thing, studying is another. Interstellar objects move fast, tens of kilometers per second relative to the Sun. By the time we spot them, analyze their orbits, and plan follow-up observations, they're often already leaving. Oumuamua was on its way out when we discovered it. We got one good look, and then it faded into the distance, too faint to observe. 2I Borisov we caught inbound, which gave us months to study it. Telescopes around the world pointed at it. We got spectra-like curves, detailed observations. That's the ideal scenario. 3I Atlas. We also caught relatively early. We're getting good data, but soon it will reach perihelion swing around the Sun and head back into the darkness. And then it's gone forever.
Unless we intercept it. There are proposals for interstellar object intercept missions, spacecraft designed to launch quickly accelerate hard rendezvous with an interstellar visitor while it's still in the inner solar system. The technical challenges are enormous. You'd need a spacecraft on standby ready to launch on short notice. You'd need powerful propulsion to match the object's velocity. And you'd need instruments capable of analyzing composition structure, maybe even collecting samples. But the payoff would be extraordinary. Imagine landing on an interstellar comet, drilling into its surface, collecting ice and rock from another star system, bringing it back to Earth for analysis in laboratories. The science we could do with that material is almost unimaginable. We could determine precise isotopic ratios, which tell you about nuclear processes in the parent star. We could analyze complex organic molecules in ways you can't do remotely. We could search for amino acids for prebiotic chemistry, maybe even for fossilized microbes if we're incredibly lucky. Even if we don't find life, we'd learn about the chemistry of alien planetary systems in exquisite detail. Every molecule, every mineral, every isotope would be a clue. Some scientists are already planning such missions. Concepts exist, budgets are being proposed. It's not science fiction, it's engineering. Hard engineering, but doable. In 50 years, maybe 100, we might have cataloged hundreds of interstellar objects. We might have intercepted a dozen. We might have returned samples from half a dozen. And with that data, we'd have a comprehensive understanding of galactic comet populations, planetary system diversity, maybe even the prevalence of life's building blocks in the galaxy. 3i Atlas is a preview, a glimpse of what's possible. It's showing us that interstellar comets aren't just rare curiosities. They're common, they're everywhere, and they're carrying information we desperately want. The unseen population is out there, tumbling through the dark, waiting for us to find them. And we will. One by one, we'll catalog them, study them, and piece together the puzzle of how planetary systems form, how chemistry varies across the galaxy, and maybe how common life really is. The library is vast. We've only read 3 entries, but we're learning the language. And soon we'll read more. Let's zoom out. Let's look at the bigger picture. Because 3i Atlas isn't the only weird thing happening in astronomy right now. Not by a long shot. Odd radio circles, mysterious rings of radio emission, origin unknown, fast radio bursts, millisecond duration pulses of radio energy from distant galaxies, mechanism debated, Tabby's star, bizarre dimming patterns not fully explained. Oumuamua, interstellar object with anomalous acceleration, 3i Atlas, comet with impossible water production and metal anomalies. And those are just the high-profile cases. There are dozens, maybe hundreds of lesser-known anomalies, transient events that don't fit known categories, spectral features that shouldn't exist, objects moving in ways that defy easy explanation. Astronomy is awash in things that don't make sense, and that's new. For most of the 20th century, astronomy was data-starved. You pointed a telescope at something, took a photograph or a spectrum, and spent months analyzing it. Discoveries were rare. Anomalies were even rarer. When something weird showed up, it got intense scrutiny because there wasn't much else competing for attention. Now we're drowning in data. Automated surveys generate terabytes every night. Sky surveys catalog billions of objects. Gravitational wave detectors record mergers. Radio telescopes scan the sky continuously. We're detecting more stuff than we can possibly follow up on. And with high volume comes high anomaly rates. If you look at 1 billion objects, even if only 1 in 1,000,000 is weird, that's 1,000 anomalies. Most will turn out to be instrumental artifacts, data glitches, misclassifications, but some will be real. And sorting through them takes time. We're in an era where anomalies outpace theory. We're finding things faster than we can explain them, and that's both exciting and dangerous. Exciting because new phenomena drive new physics. The discovery of pulsars, of gamma-ray bursts, of gravitational waves, all started with unexplained observations. Anomalies are where breakthroughs happen, but dangerous because hype cycles can spin out of control. Every anomaly gets hyped as potentially revolutionary. Alien megastructure, warp drive signatures, wormholes, dark matter interactions. The media loves it, the public loves it, and then 9 times out of 10 the anomaly gets explained by something prosaic. Dust clouds, instrumental noise, misidentified known objects. The danger is credibility erosion. People hear potentially alien a dozen times and actually just dust a dozen times, and they stop trusting scientists. They start to think science is just wild speculation. Or worse, they double down on the alien explanation, deciding scientists are covering something up. Tabby's star is the cautionary tale. When the alien megastructure hypothesis made headlines, the public latched onto it. Social media exploded, news articles ran with it, and when follow-up observations showed wavelength-dependent dimming indicating dust, not solid structures, there was backlash. Some people accepted the explanation. Others insisted the scientists were wrong or lying. But here's the thing. Tabby's star is still interesting. The dust explanation doesn't fully account for all the observations. Long-term monitoring shows complex variability. It's a weird star, possibly surrounded by a debris disk from a planetary collision, possibly doing something we don't entirely understand yet. It's still science. Still valuable. Just not aliens. The lesson is that anomalies are opportunities. They push us to refine models, to consider new mechanisms, to challenge assumptions. Even when they don't revolutionize physics, they advance it. Oumuamua's acceleration, even if it's just outgassing forced cometary scientists to think harder about sublimation at low temperatures, about exotic ices, about surface properties. That's progress. 3I Atlas is another opportunity. Its water production challenges our understanding of volatile activation distances. Its nickel anomaly forces us to think about metal chemistry in comets, something we've largely ignored because our comets don't show strong metal emissions. Its carbon dioxide dominance opens questions about protoplanetary disk conditions in other systems.
When you stack enough anomalies, patterns can emerge. Maybe odd radio circles and fast radio bursts are related, both involving energetic outflows from galactic centers. Maybe interstellar objects like Oumuamua and 3I Atlas represent distinct populations with different formation mechanisms. Maybe the transient zoo of astronomical phenomena is telling us something fundamental about how energetic the universe really is. Or maybe not. Maybe they're all unrelated. Individual quirks that happen to occur in the same few decades because we finally have the technology to detect them. Either answer is informative. The key is maintaining skepticism and wonder simultaneously. You can be excited about an anomaly without claiming it rewrites physics. You can investigate weird possibilities without becoming wedded to them. You can change your mind when new evidence arrives. This is where good science communication matters.
When reporting on 3I Atlas, responsible journalists and scientists should say, "This comet is behaving unusually. We're investigating several possible explanations. Here's what we know so far." Not "alien comet violates laws of physics." Not "scientists baffled by impossible object." But nuance doesn't generate clicks. Careful language doesn't go viral, and so the hype machine grinds on turning every anomaly into a potential revolution, setting up disappointment when the mundane explanation arrives. The solution isn't to stop reporting on anomalies. The solution is to be honest about uncertainty, to present multiple hypotheses, to update when evidence changes. Treat the public like adults who can handle ambiguity, because they can. Most people understand that science is a process, that answers evolve, that "we don't know yet" is a perfectly acceptable response. 3I Atlas is one anomaly in a stack. It's important, it's fascinating, but it's not proof of anything yet. It's a data point, a mystery, an opportunity to learn. And whether it ends up being a weird, natural comet or something we've never seen before, the process of studying it, of testing hypotheses, of ruling out explanations, is valuable. That process is science. And science, when done honestly, is one of humanity's greatest achievements, even when, especially when it's grappling with things it doesn't yet understand. Humility. Before scale, Three-Eye Atlas traveled thousands of light years to reach us. Possibly 7 billion years old, older than our solar system by more than 2 billion years. Carrying chemistry from an epoch of the galaxy we can only imagine. Think about that temporal scale. Human civilization is maybe 10,000 years old if we're generous. Modern science is a few hundred years old. The entire history of humans looking through telescopes at the universe is a cosmic eye blink.
And here comes this comet, a wanderer from deep time carrying ice that froze solid before our sun even ignited. It puts us in our place. We are not the center of the universe. We are not the culmination of cosmic history. We are recent arrivals. Brief local phenomena, and that's humbling in the best possible way, because it means the universe doesn't revolve around us. The story was unfolding long before we arrived, and it will continue long after we're gone. We're participants, yes, but not the protagonists. Three-Eye Atlas carries the ashes of stars that died before our sun was born. It carries water that witnessed the galaxy's youth. It carries memories, chemical memories of conditions we'll never directly observe. That should make us humble. It should make us careful with our claims, cautious with our certainty, but it should also fill us with wonder, because we, these brief local phenomena, have figured out how to read those chemical memories. Through spectroscopy and mathematics and stubborn curiosity, we can decode messages written billions of years ago in a language of atoms. That's extraordinary, the mirror of consciousness. Carl Jung, the great psychologist, wrote, "Who looks outside dreams, who looks inside awakens." When we look at Three-Eye Atlas, we're dreaming outward. We're projecting our hopes and questions onto this cosmic wanderer. We're seeing in its behavior a reflection of our own struggles, with understanding meaning our place in the vastness. But perhaps the act of looking outward helps us awaken inward. Think about it this way: every mystery we encounter outside forces us to confront mysteries inside. What is knowledge? What does it mean to understand something? How do we distinguish between what we know and what we wish to be true? Three-Eye Atlas is a mirror, not because it's reflecting light, though it is, but because it's reflecting us back to ourselves.
We see a comet that won't behave according to our rules, and we're forced to ask, are our rules incomplete, or are we misapplying them? We see chemistry that doesn't match our expectations, and we're forced to ask, are our expectations too narrow? Have we mistaken our local experience for universal truth? Jung talked about the unconscious as a deep well containing knowledge we've forgotten or never consciously knew. He saw symbols and archetypes as messengers from that unconscious realm. In a way, Three-Eye Atlas is an unconscious messenger too, not in the psychological sense, but in the cosmic sense. It's bringing information from a realm we've never visited, another star system, another epoch, and forcing us to integrate that information into our world view. This isn't teaching us physics alone, it's teaching us humility, teaching us to hold our models lightly, teaching us that reality is always more complex than we imagine. Existential questions. Every anomaly like Three-Eye Atlas makes us ask, are we alone? Not in the "is there alien life" sense, though that question hovers in the background, but in the deeper sense, is our chemistry unique? Is our planet unique? Is the path that led to us from protoplanetary disk to habitable planet to life to consciousness common or rare? Three-Eye Atlas has water and organics and cyanide, the building blocks of life as we know it, but no evidence of life itself. Maybe that's the universe's answer. The ingredients are common. They're scattered across the galaxy in comets and asteroids and protoplanetary disks. The chemistry of life is universal, but life itself. Consciousness, intelligence. Maybe that's rare. Maybe the step from chemistry to biology is the hard one. Maybe we're surrounded by potential life that never actualized. Or maybe life is common, but we're just looking in the wrong places or at the wrong scales. Maybe intelligence arises and falls and arises again across the galaxy, and we're in a quiet moment between civilizations. 3i Atlas doesn't answer these questions, but it makes us ask them with renewed urgency, because every interstellar visitor is a sample. And with enough samples, we start to understand the frequency of different outcomes. Water-rich systems, organic-rich systems, chemistry that could support life. We're not alone in the sense that we're connected through chemistry to the entire galaxy. The atoms in our bodies were forged in stars. The water we drink might have been delivered by comets. The organic molecules that became life on Earth might have had interstellar origins. We're not isolated. We're embedded in a cosmic web of chemistry and exchange that spans light years and eons. That's a form of connection, not the connection of communication or meeting another civilization, but the connection of shared origins, shared building blocks, building a common cosmic inheritance. The living universe speculation. Now let me venture into wild territory, pure speculation, but bear with me. What if the universe is in some sense aware, not conscious in the human sense, not a god or an intelligence, but self-aware through its observers? Every conscious being that looks up at the stars, that measures and calculates and wonders, is the universe examining itself. We are how the cosmos comes to understand its own nature. In this view, 3i Atlas isn't just an object we're observing, it's the universe sending information to itself through us. The comet is a message, we are the recipients and the medium. The act of observation is how the universe processes its own data. This is poetic, not scientific. It's philosophy, not physics. But it points to something real, the strange fact that the universe contains beings capable of understanding the universe. That matter can arrange itself into patterns that comprehend matter. That consciousness, whatever it is, emerges from unconscious processes. We don't understand why, we don't understand how, but the fact remains, we are matter that understands matter. We are the universe aware of itself. And when we look at 3i Atlas, when we decode its chemistry trace, its trajectory, marvel at its behavior, we are participating in that cosmic self-awareness. Perhaps the most extraordinary thing 3i Atlas has done isn't the water release or the nickel anomaly or the impossible activity. Perhaps the most extraordinary thing is this. It made us remember that we too are part of something alive. Not alive in the biological sense, but alive in the sense of dynamic, changing, evolving, creating complexity and pattern and meaning. The universe isn't a dead mechanism grinding away according to fixed laws. It's a living process. Creating, destroying, transforming. And we're part of that process. 3i Atlas is part of that process too.
A wanderer from deep time carrying ancient chemistry, awakening to warmth again after billions of years of cold. In its awakening, we see ourselves. Brief sparks of consciousness arising from matter, looking out at the cosmos, recognizing our own reflection in the strange and beautiful phenomena we encounter. That's the deepest implication. Not just that comets can be weird, but that weirdness, mystery, and wonder are fundamental to what the universe is. And we're privileged, impossibly, improbably privileged to be here to witness it. We've explored the science, the hypotheses, the philosophy. Now let's talk about how we think about all this, how we maintain intellectual honesty in an age of mysteries. The framework for responsible speculation science requires imagination, but imagination must be disciplined by evidence. Here's the framework we should use when thinking about anomalies like 3i Atlas first state, what we know for certain, the confirmed observations, the measurements multiple independent teams have verified. For 3i Atlas, that's water detection at 3.5 AU nickel emissions, carbon dioxide dominance, superlinear brightening. These are facts. Second, present leading hypotheses with appropriate weight. Organometallic compounds, explaining nickel. CO2 entrainment, explaining distant water. Thick disk origin, explaining chemistry.
These are well grounded in known physics and chemistry. Third, acknowledge speculation clearly. Panspermia implications, industrial signatures, exotic physics. These are possibilities worth considering, but they're not supported by current evidence. Finally, remain open to revision. When new data arrives, when observations change, update your beliefs. This is intellectual honesty in action. The public can handle this complexity. Most people understand that science is a process, that answers evolve, that we don't know yet is acceptable. What erodes trust is overconfidence followed by retraction, claiming certainty when you have hypothesis, saying definitely aliens and then actually dust. Better to say from the start, here's what we're seeing, here are several possible explanations, we're investigating, we'll update you as we learn more. What good science communication looks like. When reporting on 3I Atlas, responsible communication should avoid extremes. Don't say alien comet violates laws of physics. That's clickbait. It's misleading. It sets up false expectations. Don't say scientist baffled by impossible object. Scientists aren't baffled, they're intrigued. There's a difference. Baffled implies cluelessness. Intrigued implies curiosity and active investigation. Instead say, this comet is behaving unusually. We're investigating several possible explanations from exotic ice compositions to unusual formation environments. Here's what we know so far, and here's what remains unexplained. That's honest. That's accurate. And it's still interesting. Nuance doesn't have to be boring. Mystery doesn't require exaggeration. The truth about 3I Atlas is fascinating enough without hype. Distinguishing evidence levels. One of the most important skills in scientific thinking is distinguishing between different levels of certainty. Confirmed facts. These are observations that multiple independent sources have verified. For 3I Atlas water at 3.5 AU confirmed by SWIFT. Nickel emission confirmed by VLT. Hyperbolic orbit confirmed by trajectory analysis. Leading hypotheses. These are explanations that fit the data and are grounded in known physics. They're the most likely explanations, but not proven, for 3I Atlas organometallic nickel compounds. CO2 entrainment of water ice, thick disk origin. Speculative possibilities. These are ideas that are physically possible but not well supported by current evidence. Panspermia vectors, industrial contamination, exotic physics. Wild speculation. These are thought experiments with minimal evidence. Living comets, intelligent design simulation artifacts. The boundaries between these categories matter. Confusing them leads to poor thinking. Through our Atlas's water release at 3.5 AU is a confirmed fact. That it's caused by CO2 entrainment is a leading hypothesis. That it's carrying prebiotic molecules is speculative. That it's an alien probe is wild speculation. Keeping these categories clear prevents us from fooling ourselves. The skepticism-wonder balance. Here's the hard part, maintaining wonder while practicing skepticism. Skepticism without wonder becomes cynicism. You dismiss everything unusual, assume every anomaly is error or fraud, refuse to be surprised. That's not science. That's closed-mindedness. Wonder without skepticism becomes credulity. You believe every extraordinary claim, accept every wild hypothesis, see profound meaning in random coincidences. That's not science either. That's wishful thinking. The balance is hard, but it's necessary. Be excited about 3I Atlas. Be intrigued by its behavior. Marvel at its chemistry. Let yourself wonder about the implications, but demand evidence. Test hypotheses. Distinguish between what's proven and what's possible. Change your mind when the data requires it. This is the dance science does. 1 foot in imagination, 1 foot in rigor. Both are essential. 3I Atlas invites wonder. Its behavior is genuinely strange. Its chemistry doesn't match our experience. It's reasonable to speculate about exotic explanations, but speculation must be labeled as such, must be grounded in what's possible, not just what's imaginable, must yield to evidence when evidence arrives. That's intellectual integrity. That's how we honor both the mystery and the truth. The long game science is patient. Science plays the long game. We don't need to solve Three Eye Atlas's mysteries today. We don't need definitive answers by next week. We gather data. We build models. We test predictions. We refine understanding over years, decades, generations if necessary. Some questions take time to answer. Some mysteries persist because they're genuinely hard, not because we're incompetent or hiding something. The water anomaly at 3.5 AU might get explained next month when the comet reaches perihelion and we get better data, or it might take 10 years and a sample return mission. Or it might take a century and observations of dozens of interstellar comets before we understand the pattern. That's okay. The process of investigation is valuable regardless of when the answer arrives. Every observation adds to our knowledge. Every hypothesis tested, whether confirmed or ruled out, narrows the possibility space. Three Eye Atlas is teaching us, even as it puzzles us, about volatile chemistry, about metal sublimation, about compositional diversity in comets, about the limits of our models and the gaps in our understanding. That education continues whether or not we solve every mystery today, and that's the right attitude for the mystery age we're entering. Data will flood us. Anomalies will stack up. We won't solve everything immediately, but we'll keep working, keep questioning, keep refining, keep building toward understanding. That's what science is, not a collection of answers, but a method for approaching questions. Not certainty, but the honest pursuit of it. Three Eye Atlas embodies that pursuit. It's a question mark written across the sky in water vapor and nickel glow, and we're here looking up, determined to read it. So where do we go from here? What happens next in this unfolding story? Immediate next steps. Right now, as I speak these words, Three Eye Atlas is approaching perihelion, getting closer to the sun, warming up, and every week brings new observations. Telescopes around the world are watching, measuring spectra, recording brightness, analyzing gas production rates, looking for changes as the comet heats. The critical question: will iron appear? If organometallic nickel is the explanation, if selective sublimation is operating, then at some temperature threshold, iron-bearing minerals should start vaporizing. The spectrum should show iron emission lines appearing alongside the nickel. If that happens, it supports the natural chemistry explanations. It tells us the nickel anomaly was real but explicable, a matter of temperature thresholds and differential sublimation. If iron never appears, if the nickel dominates all the way to perihelion and beyond, that's more puzzling. That pushes us toward more exotic explanations. Pre-solar chemistry, unusual formation environments, chemistry we don't fully understand. We'll know soon. Perihelion is weeks or months away, depending on when you're hearing this. The data is coming. We're also watching for new emission lines. As the comet warms, new volatiles should activate. New molecules should appear in the coma. Each one tells us something about composition, about layering, about the temperature structure of the ices. Will we see ammonia, methane, complex organics? Or will Three Eye Atlas continue surprising us with molecules we didn't expect? Every observation is a piece of the puzzle, and we're assembling that puzzle in real time. Model refinement behind the scenes. Theorists are working, taking the observations and building detailed models.
They're simulating cometary ices with different compositions, testing which combinations produce the activity patterns we're seeing, calculating sublimation rates for different volatile mixtures, modeling how CO2 entrainment works at different distances. Each model makes predictions. If hypothesis X is correct, then at distance Y, we should see emission feature Z. When the observations come in, we check, does the prediction match reality? If yes, the hypothesis gains support. If no, we refine or abandon it. This is how science advances, not dramatic breakthroughs usually, just steady refinement, models getting better, understanding deepening, predictions becoming more accurate. Sky Atlas is driving that refinement, forcing us to think harder about volatile budgets, about metal chemistry in comets, about the diversity of formation environments. Whether it turns out to be revolutionary or just interesting, the process of studying it is making us better at understanding comets.
And that knowledge will apply to the next interstellar visitor, and the next, and the next. Preparing for the next visitor. Because there will be more. The galaxy is full of these wanderers. Detection technology improves yearly. The Vera Rubin Observatory is coming online with unprecedented sensitivity and sky coverage. Current estimates suggest Rubin could detect one interstellar object per month, maybe more. That's 12 per year minimum. In a decade, we'd have over 100 confirmed interstellar visitors, each one different. Each one carrying information from another star system. That's when we'll start seeing patterns, when we can do real statistics, when we can say X% of interstellar comets are water-rich, Y% are CO2 dominant, Z% show metal anomalies. With a statistical sample, we can map the diversity of planetary system chemistries. We can estimate how common different formation environments are. We can maybe even identify regions of the galaxy that produce comets with particular characteristics. The Square Kilometer Array will add radio observations, catching comets through their molecular emissions. The James Webb Space Telescope can do infrared spectroscopy on these visitors. Space-based UV telescopes can detect water even better than SWIFT. Our toolkit is expanding. Our sensitivity is increasing. Our ability to characterize these visitors is growing. But here's the dream interception, the intercept dream. Right now, we're limited to remote observations. Photons from the comet reach Earth. We analyze them. That's all we get. But imagine landing on an interstellar comet. Imagine matching its velocity, touching down on the surface, drilling into the nucleus, collecting samples, bringing them back to Earth. The science we could do would be transformative. Isotope ratios measured with laboratory precision, telling us exactly which supernovae enrich the gas cloud that formed the comet's parent star. Organic molecules analyzed in detail. Searching for amino acids, nucleobases, complex chemistry that could inform our understanding of prebiotic processes. Mineral structures examined under electron microscopes. Revealing formation conditions with a precision remote spectroscopy can never achieve. We could age date the material, determine exactly how old it is, confirm whether it's truly from the thick disk or somewhere else. We could search for pre-solar grains minerals that formed before the solar system and got incorporated into the comet. These grains are time capsules from stellar environments we can only imagine. All of this is technically possible. The engineering is hard, but not impossible. You'd need a spacecraft on standby, rapid launch capability, powerful propulsion for velocity matching, robust instruments for analysis and sample collection. Concepts exist. Mission proposals have been written. Organizations like NASA and ESA have studied the problem. It's not science fiction, it's the next frontier of comet science. Maybe in 20 years, we'll have a mission ready to launch when the next Oumuamua appears. Maybe in 50 years, interstellar object intercepts will be routine. And then we'll really start learning what's out there. The long vision zoom out even further. Think about the century ahead. We might catalog hundreds of interstellar objects. Dozens might get detailed spectroscopic analysis. Several might get intercepted and sampled. With that data, we'll understand galactic comet populations. We'll know how chemistry varies with stellar age, stellar mass, galactic location. We'll have a map, not a physical map, but a chemical map of how planetary systems form across different environments. And from that, we might extrapolate to habitability. If water-rich comets are common, maybe habitable planets are too. If organic-rich chemistry is everywhere, maybe life's building blocks are ubiquitous. Or maybe we'll find the opposite. Maybe Earth-like chemistry is rare. Maybe we're in an unusual pocket of the galaxy where conditions happen to be just right for life. Either answer reshapes our understanding of our place in the cosmos. 3i Atlas is one data point, but it's the beginning. It's showing us what's possible, what we can learn when the galaxy sends us a message in a bottle, and we're learning to read those messages. Slowly, carefully, with rigor and wonder in equal measure. The next chapters of this story are being written now, as 3i Atlas approaches the Sun, as new instruments come online, as the next interstellar visitor is discovered. We're living in the opening pages of a much longer book, a book about humanity, learning to read the chemical language of the cosmos, learning to decode messages from star systems we'll never visit. That's extraordinary. That's worth celebrating.
And that's why 3i Atlas matters. Not just for what it is, but for what it represents, the beginning of a new era in astronomy. The era when the galaxy starts talking to us and we start understanding what it's saying. So, 3i Atlas, the comet that refuses to sleep. Let's collect what we know for certain. Water production at 3.5 astronomical units. 40 kilograms per second where water shouldn't flow. Nickel emissions blazing green without the expected iron companion. Carbon dioxide dominance 95% CO2 in a chemistry inverted from everything we've seen. Superlinear brightening suggesting switch-on behavior. Possible thick disk origin carrying ancient chemistry from before our sun existed. And what remains unexplained. The exact mechanism for distant water activity. The cause of nickel-iron decoupling. The formation scenario that produces such CO2 richness. Whether iron will appear at perihelion or stay hidden. Is it alive? Poetically, maybe? In its dynamic behavior, its responsiveness to sunlight, its refusal to be dormant, there's something that feels vital. But literally, almost certainly not. No biology, no metabolism, no reproduction.
Just physics and chemistry operating under conditions we haven't encountered before. Most likely this is a natural comet, formed under very different conditions from our solar system, carrying composition from a different stellar environment, showing us chemistry we haven't seen because we've only ever studied one planetary system's comets in detail. The organometallic hypothesis seems promising for the nickel. The CO2 entrainment model could explain the distant water. The thick disk origin might account for the unusual abundances. But we don't know yet. Not for certain, and that's okay. The value of 3i Atlas isn't in having all the answers. It's in asking better questions, in showing us that our models are incomplete, in revealing that the universe contains more variety than our local experience suggested. Every interstellar visitor expands our understanding, not always by confirming what we thought, but by challenging it.
By forcing us to think harder, imagine more broadly, test more rigorously. 3i Atlas came from somewhere out there across light years and eons, carrying a message written in water and nickel and cyanide. We're listening, we're watching, we're learning. And in that stubborn insistence on understanding, we find something that might be the closest thing to alive in this whole story. Not the comet, but us. Curious, wondering, reaching out to touch the cosmos with our minds and instruments. The universe keeps sending these letters, these cosmic postcards, visitors from other star systems, fragments of alien worlds, messages in bottles cast into the galactic ocean. And every time one arrives, we're reminded we live in a vast, ancient, incomprehensibly rich cosmos that will forever outpace our understanding, forever surprise us, forever offer new mysteries. 3i Atlas isn't the answer, it's the invitation.
So here's the question I leave you with tonight as you drift towards sleep, as your mind wanders through the darkness between thoughts. If the galaxy is full of these wanderers' comets carrying chemistry from thousands of star systems, each one a message in a bottle, what will we learn? When we finally decode all those messages, will they tell us we're unique? That Earth's chemistry, Earth's path to life is rare and precious. Or will they whisper that the ingredients for life, for complexity, for wonder, are scattered everywhere across the cosmos, just waiting for the right conditions to awaken? 3i Atlas doesn't answer that question, but it asks it, loudly. In a voice that carries across astronomical units and reaches us in wavelengths of light our eyes can't see, but our instruments translate into meaning. The comet will leave soon, swing around the sun, head back into the deep. We'll watch it fade until our telescopes can no longer resolve it against the background stars. And then it will be gone, back into the dark between stars, back into the ancient silence. But we'll remember it. We'll study the data for years. We'll refine our models. We'll compare it to the next visitor and the next, and slowly, carefully, we'll piece together the story of how diverse planetary chemistry can be, how varied the conditions are across the galaxy, how many different ways matter can arrange itself given different stars, different temperatures, different epochs. That story will take generations to tell. We're writing the opening chapters now. Future astronomers will write the rest, but we're here, we're watching, we're part of it. And that matters, not to the universe perhaps. The cosmos doesn't care whether we notice it or not, but it matters to us, to be alive at a time when humanity is learning to read cosmic messages, to have telescopes and spectrographs and the mathematical language to decode what we see, to look up and recognize that the strange green glow in the darkness is a visitor from another star's children come to show us how different elsewhere can be. Sleep well. And when you wake, remember, the universe is bigger and stranger and more wonderful than we imagine. And somewhere out there, another wanderer is already on its way, carrying another message we've not yet learned to read. Will you be watching when it arrives?